Hello, everyone, and welcome to today's episode of Science in Action. I hope you're all having a great day. My name is Emily, and my pronouns are she and her, and I will be your moderator during this session. So that means that if you have any predictions to share with our educator, I will be the person to relay that information to them. Now, if you are interested in leaving predictions today, all you have to do is click on the Q&A box that is at the bottom of your screen. Also, we may have time to take a couple questions. So if you have any good questions you want to ask about the experiment, you can leave those there as well. Please know that if you're watching this on Facebook, we cannot take your questions from that platform. So if you do want to share predictions, then you'll have to click on the Zoom link that is in the caption of that video on Facebook. We're also offering closed captions. So if you would like to see captions, you can click on the closed caption button at the bottom of your screen and then select captions. So with that, to invite my educator to turn on camera and microphone. She will introduce herself and then we'll get started. Thank you, everyone.
Thank you, Emily. Welcome. My name is Janine, and I'm so happy you all can be here today. Most often you'll find me at the museum teaching from one of our stages, but today we're in the corner of my bedroom. So I'm just going to check with Emily and make sure everything is going okay with our broadcast. I see she's frozen on my screen. I want to make sure that I'm not frozen out there in the world.
Yeah, Janine, you look okay to me. Can you hear my voice all right?
Yes, I can hear you.
Okay, very good.
Okay, I just wanted to make sure I wasn't weirdly frozen. Okay, with that out of the way, yeah, we're here for fantastic forces. We're going to be exploring the world of pushes and pulls. And forces can move objects that are big or small. They can get things moving fast or slow. They can move things in dramatic ways, spinning, twirling. But today, we're really going to be thinking about things not moving. Forces that help objects remain at rest. And we're going to kind of, well, have some fun with a challenge, hopefully keeping our object at rest. So our object today is going to be a marker. So I've got here just a regular marker. It's kind of got a big fat end. And we're going to try to keep this object at rest the whole time. All right, so we're going to be switching cameras so we can see what's going on here. But we have our marker, and we're also going to be using a piece of paper. So this is just a half a sheet of paper that I cut out. So those are the two things you might need if you want to try this yourself, a marker and a piece of paper. And I'm going to go ahead and switch my screen so you can see how to set this up. Switch my cameras. All right, so I've got my marker. I've got my half a sheet of paper. And I'm going to put my half a sheet of paper right on my tabletop. So it's half on and half off the table. And I'm going to put my marker right in the middle. All right, Emily, can you see that okay?
Yes, I can. Thank you.
Okay, good. All right, so that's our setup. And before we do anything, right now there are some forces acting on the marker and the paper, keeping them at rest, not moving. And I'm sure from your everyday experience out there, viewers, you know exactly what forces I'm thinking about. So if you know what force I'm thinking about that helps keep objects not moving, go ahead and put it in the chat box. Say it to the person next to you. And I'll just look at my marker for a moment.
So Janine, we have a bunch of people typing in essentially the same answer. So for example, Anna, age 12, thinks that gravity is the force that you're talking about. Same with Michael, age 9. Everyone is saying gravity.
Yeah, exactly. Gravity is all around us all the time. And it's a force. It's a force that acts on the mass of objects. So our marker definitely has mass. And anything with mass is pulled toward, well, other things with mass. And of course, under our feet, Earth is a giant thing. It has a huge amount of mass. So our marker is being pulled toward the mass of planet Earth. Okay, so there's a pull there. Now there's a second force. One that might not be as obvious to us. There's a second force helping the marker and the paper remain at rest. The table. If the table somehow disappeared, what do you think would happen to the marker? Yeah, if you want to put that in the chat box, go for it. I know it's a really obvious thing. If the table somehow disappeared, we know from our experience exactly what would happen to that marker, right?
Yeah, absolutely. Everyone is saying that those things would fall to the floor.
Right. So they would fall right to the floor. So our table is pushing back. So we have gravity pulling down, table pushing back. Those two forces are in balance. Okay. And this is good information for us, because when things are balanced like that, when forces are balanced, objects remain at rest. So the forces acting on our marker right now are balanced. And this is great, because for our challenge, we want to keep this marker at rest, not moving. But for our challenge, we want to try to get the paper out from underneath the marker. So we have to pull on the paper in some way, or push on it, move it, apply a force to it, but somehow keep the marker at rest. And when I say at rest, I mean the marker is going to remain upright like it is right now. We can't touch the marker in any way with our hands, and we have to get the paper out from under. So think about that for a moment. And if you have an idea about how I should move the paper, what kind of force, and how I should apply that force to the paper, go ahead and share it. And we'll try out some of your suggestions.
Okay, so let's see. Got a bunch of things coming in. Will, age 8, thinks that you should pull on the paper. Nicole specifically says that you could pull it very quickly. I have a bunch of people saying it, do it really fast. Same with Anna, age 12.
Okay, so we should pull on the paper. Yeah, we have to pull on the paper in some way to get it to move, but hopefully keep the marker at rest. All right, so I hear a bunch of people saying fast, and I heard someone just say pull. So the first thing I'm gonna do is I'm gonna hold on to the edge of the paper here, and I'm gonna pull. And we'll just see what happens. So I want you to make an observation, and then we'll go from there. Okay, so here we go. 3, 2, 1.
Oh no.
Yeah, it fell over, didn't it? All right. So I know people are saying quick, and I bet they're thinking with my son when they say quick, like super duper, as fast as you can, lightning fast quick. All right, so I'm gonna try it as fast as I can. I'm actually gonna stand up for this. Okay. All right. Were there any other suggestions out there besides fast?
Yeah, some people have been saying maybe you could pull it nice and slowly. Someone says roll the paper slowly.
Okay.
A few people are saying roll it.
Yeah, no, I like those. I think we should try all of that. You know, we're using our everyday experience here, the way objects move around us. So we tried fast and that didn't really work out. So we'll try slow. And I like the idea of rolling it. But I'll just try slow first, and then we'll try rolling it after that. So I'm just gonna go as slowly as I can. So I'm gonna apply my force very slowly. What's happening to the paper?
It looks to me like it's bringing the marker with it.
Yeah, both of them are moving. And of course, if I keep going, our marker is gonna fall right off the edge here. All right, so that was as slowly as I could. And I'm gonna try to roll it. So I'm just gonna kind of roll up the end as I go. And let's see what happens here.
Janine, when you're done with that, I think I have one more really good idea from someone else on the chat.
Oh, goodness. All right, so that's moving as well. All right, so what's the other good idea?
So we have an anonymous attendee that says, could you pull it down?
Can I pull it down? And I like that thought. I like that thought because they're probably thinking about there are a couple things going on here. You know, the bottom of the marker and the piece of paper are in contact with one another. So there's kind of a hidden force there. And I bet some of you, now that I've mentioned it, that we have two things that are in contact. And as I try to move the paper, the marker is basically rubbing up against the paper. And if you have two things that rub together, there's a force there. And that force if we rub our hands together, you feel the result of that force. Your hands start to get warm. We have friction to deal with. And by going down, changing our direction, maybe that'll help. All right, we're gonna stop for a second. I'm gonna put this aside. And we're gonna make things a little bit bigger to explore this idea of pulling down. So I've got a tablecloth and a big can of veggies. Now, like our marker and our paper, if I do this really slowly, we're probably gonna see the same result, but let's just verify. All right, I'm pulling as slowly as I can here. And yes, that can's starting to move. And of course, if I pull as quickly as I can, but I pull straight out, it also starts to move. But if I pull down, let's see if we get something else happening. So I want you to watch carefully how I do this. I'm gonna pull down as quickly as I can. Here we go. I'm gonna stand up here. 3, 2, 1. Did you see that?
Wow.
My hands are pretty much at rest, not moving. I'm gonna do it one more time so you can see here, by pulling down, we applied our force quickly, but the direction really matters too. 3, 2, 1. So now that we have that knowledge, we've made that observation. Let's go back to our marker and our paper. Because by pulling down and quickly, we give friction just a little bit of time to act instead of a long time to act. And that's the key for this. Not just what forces are there, what forces we apply, but how long those forces last and the direction of the force. So friends, are you ready for me to try this? I'm gonna go down as quickly as I can. Like basically straight down through the paper. All right, here we go. 3, 2, 1.
Good job, Janine.
Thank you. Now my paper is here on the floor now. I got it. Yeah, now to make this a real experiment, you can start changing variables. You could add a second marker to see if that's more difficult. If you could do the same thing, you could change the size of the paper. Is a bigger piece of paper or a smaller piece of the paper more difficult? Or you could try a different object. Earlier today, I was exploring this little can here, which is just a plastic can of bay leaves. But you can see it's got a bigger bottom than our markers. Does more surface area in contact with the paper make it more difficult or less difficult to get that paper out from underneath? How do you have to apply your force? All right, now I'm gonna switch back to my other camera here, because I bet some people may have a question or two or an observation they may have noticed while things were going on.
Yeah, I have a couple. This one isn't so much a question, but I think that you might have a really good response to it. Honor, age 11, says that it's not working for them. So could you give any advice to someone like that?
Yeah, so one of the things you need to do is go straight down, but also you might have noticed, like I put my hand kind of up high to start. So if you give yourself the most range of motion you have with your hand, sort of a karate chop situation, that might help. Of course, as you're moving your hand that fast, make sure you're not going to hit your hand on the edge of the table or anything underneath that area. So you want to kind of bring your hand up high and then bring it down as quickly as you can. Of course, you can try things like moving where the marker is. Put it closer to the edge of the paper, away from, or toward the edge furthest from the edge of the table. So you have the least amount of paper underneath to kind of get your technique down. And once you get good at it, then you can maybe put more paper underneath.
Cool. Thank you, Janine. I imagine a lot of practice is necessary too, to become a master of it.
Yeah, yes. Also, the kind of paper can matter. Like I've got here, this is printer paper. So if you've got more like a notebook paper, that might make a difference. So you can try different kinds of paper and see how that affects things.
Okay, cool. Thank you. Earlier in the program, Max, age 6, asked if gravity was a force. And I know you already explained that, but they might have missed it.
Yeah, so yeah, gravity is definitely a force. It's a force that acts all around us all the time. And you know, the funny thing about forces, we often forget this, they're invisible, but they affect objects' motion. So how they move, how fast or slow, and they affect, you can apply forces by pushing and pulling on things, but gravity, of course, is a force that's acting all the time.
Cool. Now I'm also seeing that Killian is having great success with this experiment, and they say thank you.
Okay.
Gianna asks, does cardboard work for this experiment?
That would be definitely something I would love to try. I've never tried it with cardboard. I would imagine cardboard's pretty stiff, so that might affect the way it moves and how it applies its force to the marker. Because remember, the marker and paper are applying forces to one another, and your hand is applying the force to, in that case, the cardboard. I would love to try something like a brown paper bag, cutting up a brown paper bag and seeing how that would work. That might be something else that you could try.
Cool. Someone asked earlier about the 3 laws of motion. Is this concept of inertia related to them at all?
Oh, yes. Yeah, what we just witnessed is really a great example of Newton's first law of motion, which is another way of thinking about inertia. And the first law of motion, often when you read it or hear about it, talks about an object at rest will remain at rest unless acted on by an outside unbalanced force. And so our marker, of course, was remaining at rest because we had forces that were balanced. And when the forces became unbalanced, that's when the marker started to move. And the weird thing about that first law, it has a second part, that an object that's moving will move forever and ever and ever in the direction that it's moving unless acted on by a force. And of course, here on planet Earth, there are forces all around us that affect the object's motion. So we don't see things just continually move in the same way. There's, you know, gravity, friction, air resistance, even just bumping into something else.
Nice. This is kind of related to that. You just mentioned the forces that exist on this planet. Nick, age 9, asks, does zero gravity mean that there are no forces acting on you? So this is not thinking about our planet.
Yeah, so out in space, if you were far enough away from any big masses, it would just be your mass and nothing pulling on you. Now, of course, there would be maybe some other forces if there was another object, even if it was small, and you pushed against it and it pushed against you, that would affect your motion. So even if there's zero gravity, even especially if you're watching something like our astronauts who are orbiting our planet, there are still forces acting on them. They do move around and they change their motion. But of course, gravity is a lot less up there in orbit. Almost non-existent from planet Earth. But yeah, so depending on what's around you, what other masses, whether they're big or small, that could affect your motion.
All right. Janine, I think we have basically one more cool question about forces in general. Not in general, but connected to your experiment. Someone asked if there are any other forces acting in your experiment besides
Emily, I think I lost you
and...
there. I didn't quite hear the question.
Oh, sorry. Can you hear me now? Janine, hello? Hello, hello. Testing, testing.
I can hear you now.
Okay, sorry about that. Someone asked, are there any other forces besides friction and gravity acting in your experiment?
Friction and gravity. Well, once I started pulling on the paper, there was the forces I was applying. So the pushes or pulls in this case, I was applying with my fingers. And of course the tabletop has its own friction between the paper and the table is another thing to think about. So that would be the big ones.
Okay, very good. So I'm going to turn my video back on. Hello again, everyone. Janine, we had so many wonderful predictions and responses, and we had a ton of people asking if various materials would work for that experiment. But I think the best advice that you could give is just to try whatever you have and see what happens to it.
Yeah, I mean, I used, this marker here I had in my house, but any object you have that could stand upright that would be kind of tippy might be fun to try. Of course, things that aren't breakable would be a good thing to work with. But you could make a stack with vegetable cans and try different materials, trying to get it out from underneath that. That might be fun.
Awesome. Thank you so much, Janine. We're almost out of time, everyone, so we are going to wrap it up here. Janine, do you want to say a final goodbye to everyone before you go away?
Yeah, thanks for joining us. I hope to see you again soon. Awesome. Bye-bye.
Thanks, Janine. All right, so folks, I'm going to start to show you another screen just to say goodbye. And again, thank you so much for joining us today. If any of you do these experiments or try these experiments and take photos and put them on social media, we would love it if you could use the hashtag #MOSAtHome so that we can actually see what you're up to, because that's the whole reason why we're out here doing these experiments with you. We would love to see those. If you're interested in seeing any of our other virtual content, you can check out mos.org/MOSAtHome. And then finally, if you enjoyed today's presentation, we encourage you to visit that bottom website that you see in order to support this MOS at Home mission. And that website is www.mos.org/Science Matters. So folks, again, thank you so much for tuning in, and we'll see you next time. Have a good one.